First is Melissa Lunden from Aclima, and she'll be talking about improved geospatial resolution with Google Street View cars. And I know we all have used Google Maps, so this will be really fascinating. Thank you.
Thank you for that introduction, and I'm really excited to be here. Thank you so much for inviting Aclima to participate. And I'm wondering how do I forward? Oh, this thing.
So the green button.
Okay.
Is to move forward.
Okay, great. And I should state before I even start that I'm now completely worried about every graph in my presentation. And I can say that they actually have several different types and color schemes, so we can vote at the end of my presentation as to which ones you felt conveyed the information the best as a learning exercise. So I'm going to talk about not just what we're doing with the Google Street View cars. I don't know, I haven't tried it yet. Yes, big success. I'm actually running these off of the web, and this is working, so that's pretty cool. I'm going to talk not just about what we're doing with the Google Street View cars, which is extremely exciting, but what we're doing with sort of what we want to call high resolution sort of environmental data in general. And so I don't need in this audience really to state the problem, but you can't manage what you can't measure. Air quality is a problem everywhere. And I mean environmental quality, but specifically like you talk about particulate matter in Delhi or in India or in China or even in the Bay Area when we had all those fires. It was absolutely horrible. And so at Aclima, we're really sort of pushing towards sort of the universal measurement of these sorts of things, sort of how can we add the operational costs of the environment into our decision making if we actually don't have those measures. And they're not simple, but we are at Aclima building a solution. We're a tech company in San Francisco, but a much, much smaller one than Google. And so sort of ubiquitous real-time sensor networks. This is something that's really coming out of the sort of tech world, academic world. It's something that's supported by cloud, advances in sensor technology, advances in communication technology. So all of these things coming together is this great moment to support this. And we like to call it environmental intelligence, what we're trying to provide. And we think of a number of different ways that it can inform different aspects of, sort of what we do, both sort of from a business point of view, but also from a health and making better decisions point of view. And so our platform is we don't just make a thing because the data is hard, and making sure that what's created is hard. And so we build the devices and the network, but then you also have to build the data infrastructure. This is big data. It's not simple. I think people in this room understand that, but I'll talk with the scientists that will put out 20 sensors, and that still fits in an Excel spreadsheet, and this stuff really doesn't. So, having to build the back-end infrastructure, the ontologies, which as a word I can use now, and then the analytics background in terms of like, how do we ping that data? How do we put them together? How do we put the context in with it? So these are all like really big challenges, and it's really exciting to work at a workplace where we go from the physical scientists all the way through sort of the visualization people. And then, of course, so what we're hoping to provide then is this environmental intelligence as a service. We're not just giving you the measurement, but we're helping you understand the measurements and integrate it into what you are trying to do as a user. And so we have multiple deployment platforms because the air is bad in many places. Indoors is where we started with a 500 node network at Google's in Google's buildings, and then working on for outdoor stationary and outdoor mobile. And you can see outdoor mobile, that's what's really caught a lot of attention because it is pretty cool. It's a Google Street View car. You're driving around, you're measuring air quality. It's the first project I started working on when I came to Aclima a little over 4 years ago, and it was like the dream job. Although I was testing the mobile car driving around Mountain View, and I had to remember that I was in this like huge branded car and not to sort of do what you would normally do in a car when someone makes you angry. So some interesting things to learn, or learnings, as we say now in the tech word, learnings. And so I first want to talk about our indoor atmosphere, and I'm actually heartened to see some of the slides that people are actually understand that the indoors is important, because in the atmospheric community, all of our laws are based on outdoor measurements, and that's obvious because those are where we take the measurements, and that's how we do the epidemiology and the health studies. But we're indoors 90% of the time. And indoor pollution levels can be much higher than outdoors, especially in sort of the United States, which is generally clean compared to a lot of the rest of the world. And there's some simple measures and some simple sort of chemicals, if you will, have been found to link sort of building design, how we design our spaces, to our health, our well-being, our stress levels, our cognitive function. And so, for instance, carbon dioxide levels above 1,000 ppm are considered to, you can start seeing decays in your cognitive performance at that concentration. And I can tell you that concentration is actually pretty small and pretty easy to get at. And I wouldn't be surprised if later in the afternoon or in the morning in this room we actually exceeded it. You certainly do in your conference rooms. You do in your cars. Okay, I'm just going to say this. When you push the air condition button and your car immediately goes to recirculate, change that right away, because you can get to OSHA level CO2 concentrations in your car in a matter of minutes. So that's just a safety tip. And so better air indoors leads people to make better decisions, makes them healthier, makes them happier. And so we're sort of considering this as mapping the indoors. And this is some data just down the street, 1800F. We were doing some work with the University of Arizona and the GSA, combining health measures, actually just heart rate variability, with indoor measures of the environment, and coming up with some really interesting research results from that study. And so this is just a map of all the different conference rooms that we measured in that space, and you really can see the ones that stick out. Maybe those are the ones that are used well, maybe those are the ones that the building is just not supporting well enough. But when you really start to map out the indoor space and look at it from a place where you're combining the building data as well as this data and understanding the health effects, you start to really understand how you need to design or modify your spaces. And in particular schools, this is from a network that we're starting to engage with some schools where, the kids take a test at the end of a quarter or at the end of what have you, and you can sort of look at the different classrooms they were in and what their exposures to, get to simple things, noise, light, CO2, look at exposures to that and how that affects like our cognitive function. And so this is a naturally ventilated school, which is something we want to get at. We want to not use as much energy. But the CO2 concentrations got as high as 3,500 ppm on a regular basis in this schoolroom. That is not where I would want to be learning. And sometimes it can even get to 5,000, which again is the sort of the OSHA standard. I don't know if it's 1 hour, 8 hours. I can't remember all those different sheets, but nonetheless, a bad situation. And if you're not measuring it, you're not going to know that. CO2 is invisible. Sound is not, but we still, to know what really is a problem, you have to measure it. And if you think about comfort in a building, comfort is more than just, I'm comfortable standing here, the temperature's okay, I can kind of see. It really does affect our performance and our health. And so I like putting this up. Buildings are great, but you put people in them, they do things to them, and the negative experiences have like a really big impact. And so this is a great building occupation satisfaction survey from the Center for the Built Environment. And you can see noise, temperature, sound, privacy, and a little bit of air quality are the things that stick out. And I'm sure if we took a vote here, all of those things would also stick out, especially if you're in the modern open plan kinds of offices, which people are moving to for a variety of reasons. So this is an NIH building in Bethesda. And you can see, so this is just a temperature map, a simple temperature map. And it's, you can see the time. It's now midnight, it's 3 a.m., it's 4 a.m. And you can see as this is in the summer and the cooling starts to come on, there's a place right there in the middle. Well, first of all, you can see there's almost a 5 or 6 or 7 degree Celsius difference across this building. And then during the daytime, you can see that spot that's right in the center. That is a part of the building that never gets above 19 degrees Celsius. That's actually pretty cold. And so, yes, the discomfort you've had in buildings is something that it's true, and we can measure it. Now, then we have to take that and do something with it, which isn't trivial, but still, having this kind of data is really important. And again, even simple things like temperature, sound, light. So moving on to sort of urban air quality, it's a global health problem. Don't need to say that in this room. And you can see that a lot of places in the world have city-level annual PM2.5 concentrations that are just incredibly high. 92% of residents experience high, poor urban air quality. It results in a large number of premature deaths per year. And this is the current situation in a good part of the world. This is the Bay Area. And so all of those purple dots are a regulatory network that supports the EPA regulatory sort of network that run by the Bay Area Air Quality Management District. And so I think there's like 15 that give sort of air quality measures that you would sort of traditionally think of. And then this is the kind of modeling that happens there over on the right-hand side. That happens to be an AQI model from one of the days the fire was running. So that was like a really, really bad day. But nonetheless, that's a pretty broad spatial pattern. So if you're in Berkeley or in Oakland, it's saying you're getting the same PM concentration. And I can tell you that's not true. So here's a map of, this is not model data. This is actual air quality data produced by our Google Street View cars. And you can see this is NO2 concentrations. And you can see on a street-by-street level that it can change from neighborhood census tracts, even from one block to the next. And so, exposure is hyperlocal, it's complex, it's heterogeneous, and it's very great to really be able to try to capture this now. And so this is our mobile platform. We are measuring sort of the typical pollutants, ozone, NO and NO2, black carbon, which is soot. Oftentimes it's a marker for soot from diesel buses or other sources. And then particles, ultrafine particles, and particle number. We're taking 1 second samples because 1 second you're down the road, you've actually traveled quite a bit. And the data that I'm showing is actually from what we call reference equipment, and we have our sensor-based platform in the car at the same time, whereas we develop the lower cost platform that we will start to scale to tens and hundreds of cars as opposed to what we started here with this fleet. And so we have the platform, it's driving around, we get the data streamed in live time so I can actually see what the car just drove through. It's just actually kind of fun. And then drivers give a map, and it's sort of like playing around with different ways to sample the city. Now that is a statistical problem or opportunity that's super interesting. How many times do you need to drive down a particular street to get a stable solution for what the concentration is on that street? And how can you optimize that to not have to drive as much but still get the map that you want? And then drivers, Street View drivers are it's actually kind of a relatively low-paid job. So how can you give the drivers the information they need to drive around this sort of pretty high-tech instrumentation and give them a map that tells them how they should sample the city when I will tell you, mapping tools, aside from telling you to get from here to there, if you want to design a drive that's turn by turn, there actually are no tools that can do that, which is remarkable. But nonetheless, what Google does is they just say drive every street in this block, and then and then you do that, and then it tells you move on to the next block because it's a mapping platform. We're combining it with air quality and thinking about different ways to sample. And so we're really sort of hoping to drive science, health, urban planning. How can we make our cities healthier? This was the big breakthrough paper that came out in June of this year that talked about our mapping work in Oakland. And so this is a part of West Oakland and downtown Oakland. There's a port over here on the left-hand side, a number of major freeways, and a number of industrial. The West Oakland area is sort of mixed industrial and homes. So really interesting, some interesting possible exposures there. So this initial research approach is let's oversample, and then we can kind of see what we need to do. We repeatedly drove each street, calculate the pollutants by like 30-meter segments, and you can and what you get is demonstrated spatial patterns. So here, just a zoom into some of that area of West Oakland, and you can see over here in that box is a part of West Oakland where, in this case, the concentrations of NO and black carbon are extremely high. And there, you look at this map, you can see the source there, metals recycling facility, and you're like, okay, obviously. But if a priori, you probably couldn't have at least guessed what these concentrations were. And so the results from this mapping showed that from one end of the block to another block, or just a few feet, you could have a difference in concentrations from 5 to 8 times, which is pretty substantial. And of course, the levels at streets are often lower than they are on freeways and things that are obvious, but then you can actually kind of quantify that. And some individual hotspots do pump out that are interesting. And then if you average the data over like all the residential streets, you actually get a value that is very close to that star in the middle, which is the West Oakland regulatory network. So when you start to average the data around this high resolution data around an area, you get a value that actually does have some connection with sort of what you're getting from a regulatory point of view, which is it's nice, but also really helpful if you think about what kind of data products you could kind of create with these sorts of data sets. And then, of course, the variability depends as a function of pollutant. Here's a whole different color schema. So this is Boyle Heights. And so you can see black carbon, NO, and NO2. There's a tremendous number of freeways around this region. It's a really active environmental justice region in Los Angeles. And so you can do interesting things like, just the statistics of the black carbon, and this is from a number of regions, Boyle Heights, in addition to Wilmington and West. And you can see the differences in the median black carbon concentration, but you can also see how wide that distribution is. There are areas that are close to zero, and in that same city, there's a 30 or this might be 100 meter average. They're closer to 3 or 4. So that's a pretty big difference. It also allows you to maybe to go in and preferentially tackle those areas of high concentration, getting like a bigger bang for your buck if when you're starting to go and actually tackle some of these sources. And then I put the line here, that's the measurement from the closest regulatory station near Boyle Heights. And so it's giving you that one data point, and it certainly is very close to sort of the peak in the distribution for what we measured, but you can see all of this other granularity we're getting around with that kind of data. And so we've played around a bit with like how we might drive certain sorts of insights. And one real obvious one is what's the concentration of this black carbon around schools? And so this is an average, these maps show average concentrations around schools for 500 meters. And you can see actually just even the Boyle Heights region, blue is cleaner, red is dirtier, and just over a few blocks you can see there's large differences in what the black carbon concentrations are. Here's a bit of a zoom into that region. So not only can you see patterns that you expect existed, but then when you want to go in and actually start to improve in certain areas, this will tell you like where should we put our effort, and perhaps even what kind of effort should we do? Is it a gas phase problem? Is it a particle phase problem? And try some mitigation measures. So. This kind of data I find is really exciting, even though it's just aggregating sort of with location of sensitive populations. It still immediately becomes sort of actionable, if you will, in terms of directing programs that the South Coast is already supporting in terms of putting filtration into some of these schools. So I started playing around with a few other data sets, and the most obvious one is spatially resolved environmental information from a program called Cal Enviroscreen, which is supported by the Cal EPA, which Gina probably knows more about than I do. But it's actually a really great program. It's a community-based tool, census tract level, to identify areas with high pollution burden. And it combines environmental, health, and socioeconomic information all together to get at a score. And this is a green-red map, so that's probably not particularly helpful either. This is not mine, though. I did not. This comes from their tool. And these are just percentage cumulative scores, and so you really can see sort of the areas that are that kind of could use support really pop out. And here's the kind of data that's driving the model, and it's a great tool, and I don't mean to denigrate the fact that there's a lot of people that went out and collected a lot of information on some sources and other things, because there's a lot of data that goes into this model. But this is, since we're sort of talking about our pollution, the data for particulate matter comes from modeling. It's just like that map I showed you from the fire early beforehand, and you can see this is for that region, and there's that one monitor. Here's what it predicts. There's this whole region of the Bay Area that's, and this is a percentage It's not an actual concentration. That's what I was allowed to pull off of the website. So it's just sort of illustrative of the broad spatial patterns that go into that model. And then over on the right-hand side is the spatial distribution we get from our platform. Now, why is it not showing the whole region? Well, some regions we've only driven like 3 or 4 times, and so just using some sort of drive day statistics, I only highlighted the census tracts where I feel like we've had sufficient data to really give you this is a mean that is it's realistic. Some interesting things pop out. Oakland shows up like you would expect. Regions of downtown San Francisco, because there's a lot of traffic there, truck and cars, and it's this big urban space. So you get these really interesting air trapping things that happen when you emit a lot of pollutants into a box that's bounded by really tall buildings. But down here, sort of on the bottom, that is Hillsborough, and it's actually a pretty affluent suburb. And down in the flats where there's the industry and the freeways and everything, the concentrations are high, but they're much higher up there in the hills. And I've talked with a couple people that live there, and they say, yes, you can smell it. Something's happening. And that is a result of, we think right now, both some diesel buses that are kind of serving that area, but also the patterns of the meteorology, because air pollution, of course, is emissions and meteorology. Is this stuff forming, blowing away, et cetera, et cetera. So anyway, you can really see sort of, we can get that detail, and then you can do things, and this is a really simple plot, but this is the asthma data you can get from the Callan virus screen data, and it's emergency department visits per 10,000 people, and this is the 95th percentile of the NO2 concentration, and you can start to see this sort of variability that you can't tease apart, at all with that data, because there is no NO2 data in the Callan virus screen tool, but just period. And so I just did a simple linear fit there. And you can see, obviously, there's a lot of scatter, but you really can start to dig into this. And of course, asthma would have a lot of things combined into it. But here's where I made a note. Physical scientists are sort of confounded by this big data set. We usually use a spatial, sort of physical chemical models for air quality. We don't use sort of big data sets like here's the correlation, here's how we come up with things. And so it makes us uncomfortable in terms of, does this model really fit with what we already know about what's happening in the atmosphere, but we can't predict at this level with the models we have right now. And then they have mostly, I'm speaking for my cohort of engineers, for the most part, really limited statistical understanding. So if it's not a pretty simple fit, linear fit, maybe a curve that you define, so you can get that fit, you get an R squared, you get an RMSE, and you are psyched, right? And I've already heard thousands of things that I should think about from the folks in this room that are really interesting. So you think about the people that are going to stumble around in this kind of data, it's not not just the well-informed folks that really kind of understand how to get truth out of it. But as this data becomes more widely available to communities, which we want them to be able to have, that's going to be a really important consideration. So just to kind of summarize, plus I should say that the cities and public institutions are simply not set up to deal with this kind of high spatial temporal resolution data. They're not set up with tools that can access the cloud. The cloud is expensive. I so resonated with that point. Every time you go and get the data, it really can add up. So you can score multiple terabytes of data, but you can't access it very easily. So the people we really want to be able to sort of make decisions on this, put an electrified bus route down some area where that will really help lower the black carbon and NOx concentrations in a region, and then measure what's happening afterwards. That is something that they, from a data point of view, can't do, which is one of the reasons why we're sort of focusing not just on the measurements, but also delivering sort of data products as a set of tools. So just to kind of summarize, air pollution, varies spatially and temporally. Exposure patterns are extremely complex and heterogeneous, but we can actually maybe start to get at some of them here. And that's just not outdoors, but it's also indoors. And so the sensor networks, we're really sort of excited about this revolution, and that's why we're trying to push it, really will enable us to get this kind of data. And then hopefully, it's this really amazing opportunity to use alternate ways to think about mapping air quality or even climate change data with different levels of contextual data set, not just the ones that I can think of as a sort of physical air quality scientist, but also like layering in some of the health data, layering in some of the land use data. That's actually one of the things that the community does do mostly, land use regression modeling. So again, it's sort of linear statistical modeling, but in a broader, larger data set way. So I'm excited about that and the opportunities for that. And I'm particularly excited about this map. This is from the World Health Organization when they put out that pollution, it was like December of a couple of years ago. And this is the data they based their model on. So each data point is well, it's marked by sort of green, yellow, red, of course, so red being bad. And U.S. is mostly green, and Europe is pretty green with a little bit of yellow. And so I love the fact that we actually have that data, but look at all the white space. Look at all, there are places where there are no biomarkers, there's no measurement, period, right? And so the sort of low-cost sensor-based platform that we're working on to lower air quality measures by a factor of 100 to 1,000 on a Google car that routinely travels through Lima or pick your space will allow us for the first time ever to go and provide measurements in some locations. And so aside from all the really cool science and understanding and planning we can do with it, I'm also just excited to bring this data to the world at large, not just with Google, but with other fleets and other sort of partners as we start to expand this year. So with this map, I will leave you and thank you so much for having me here.
We have 1 minute for break, so I'll give you the prerogative to ask questions.
Okay, I just had a question.
Yeah.
No.
No. We have. If you demur, you'll use up your 1 minute.
Okay. So wonderful talk. Very interesting, high-resolution spatial data. When you unmoor the stationary monitors, you lose seeing what happens in a place with time, and you're moving now in both space and time and capturing snapshots. There's the issue of how do you interpret different places at different times. But the question I have is, you guys are Google. And
no, actually we're
or you work
Aclima.
with Google.
We work
You're
with
working
Google.
with Google, and Google knows where people are in space and time better than just about anybody. And that's one thing that's always a shortcoming of the epidemiology, is we don't really know where the people are with respect to it. So in your work, are you looking at combining those kind of data of
Yes, we are.
population, location?
Absolutely, we are working to integrate a number of data sets and working on sort of just the agreements to be able to do that and work together. Not just with Google, but with sort of talking about expanding with other sorts of partnerships where we can kind of help put that information together, both from a measurement point of view, but also from the layered data set. And people, absolutely. It's not an individual person and how they're walking through a city, but it is like there's a lot of people here, there's a lot of people here, and I think that's really exciting, definitely.
All right, so we have a break now. Let's thank Dr. Lunden again.